modern invention of an open symmetric design, the data encryption standard in '73, and later on went into standardization. So you see that there is a design based on principles, and then standardization and use. And then public key, there's the revolution with Diffie-Hellman and Rivest, Shamir, and Edelman, and others. And then in the early 80s, people started to realize that these people suggested crypto system, but there's no notion of trying to understand in what sense these things are secure. So people like Yao, Goldwasser, Mikali, and others started to have models, definitions, and the right notions of security, and inventing the real primitives like semantically secure encryption, signature, zero knowledge, pseudo-random generators, and so on, multi-party computations, and so on. And at that time, by the way, for people who were not hiding under a rock or under an academic shield, there was also there were also efforts to implement these things. PGP was one of the pretty good privacy, was one of the early things, cryptographic libraries. When the internet started in '94, SSL started to protect communication. Now it's everywhere. And this includes implementations in hardware, in CPUs, and so on. I mean, CPUs incorporated cryptographic primitives as a CPU, central processing unit operation. Okay. And from the mid-'70s to the mid-'90s, all these developments. So you have to be always a contrarian. You have to look at things differently. And the first point, the first bullet on this slide is something that you can apply elsewhere. If everything is so great, something is wrong. It cannot be that in 20 years we capture the world, you know, we conquer the world and everything is great. And indeed, the state of the art, and that I'm talking about mid-'90s, actually it's in one conference, Crypto 96. There were two papers back to back. One of them discovered side channel and the fact that cryptographic implementations actually leak certain physical information like timing, like energy and things like this. And then you can capture those and try to analyze what is the key. The simplest thing is that the simple exponentiation protocol. Exponentiation is used heavily. So you do it bit by bit on the exponent, and then if it's a 0, you square. If it's a 1, you square and multiply. So it costs more. And then you can try to guess where are the ones and break the key. That was Paul Kocher. Now it's an area by itself in cryptography of physically secure cryptographic operations, but also elsewhere. And back to back with it, actually the paper before it in the conference was my paper with Adam Young, where malicious cryptography was first presented. And I'll get back to it. But it's always good to be suspicious of the greatness of the field, and we just follow it with blinders. And so how is cryptography done? Modern cryptography done? You have a model, and you have a problem specification. When you define correctness properties, that the protocol or the scheme has to follow. For example, an encryption scheme, if you apply the encryption and they apply the decryption, you have to recover the same message. If it doesn't have this, it's not really an encryption, yeah. But there is also security properties. If I encrypt and you get it and you don't have the decryption key, it should look to you like a random nonsense. And these are mathematical properties that you can quantify. I'm not going to do exact definitions or proofs or anything in this talk. I'll do a lot of hand waving. And based on these properties, you do a construction. You say, okay, I have some number theoretic assumption, I do this construction, and then based on these assumptions about mathematical problems, I'm going to prove that the construction achieves the goal of the specification. This is not unique to cryptography, but this is the way it's done in cryptography. You prove correctness, typically independent of assumption, unconditionally, and you prove security typically under some complexity assumption because of the state of the art of complexity theory. We don't know if P is different from NP, so maybe all cryptography is easy in polynomial time, and so on, but under assumptions we can claim something. And then we declare victory that we apply. We have the constructions which follow the specification. And the question that was asked, is this at the mid-90s? Does this paradigm that implementations adheres or follows the specification is all that is needed, and we have the entire cryptographic field set in this direction? Now we can just need the right specifications, and we have a methodology how to achieve things. Usually it's okay, but what about when we consider security primitives when embedding it in a setting? That's first question. Or we purpose it to do something. So typically, there are going to be a specification, which is model and definition, and then there is implementation on the other hand, construction and proof, and you have to show that it follows the specification. And therefore, you consider the specification, right? The implementation to be right. And let me get off cryptography, get to something else. In computer science, in the beginning of computer science, and there is the Turing paper that it does many things. It does even practical things. My interpretation of universal Turing machine is also the invention of subroutine, but let's leave it aside. But essentially, what Turing shows that in his paper, that the Turing machine is equivalent to partial recursive function. Any partial recursive function can be implemented by a Turing machine. Any Turing machine computation can be viewed as function. And it's actually good to read these old papers because there's a lot of smartness in it. In '56, John von Neumann, apparently he was talking about it a number of years, and he was like me, it took him 3 years to write a paper. And he wrote probabilistic logics and the synthesis of reliable organisms from unreliable components. And what he claims there, and that's fantastic, and I consider this paper to be the first systems paper. I ask systems researchers, what's the first system papers? They say, maybe the Usenix paper, maybe the Multics paper. And I say, no, 56 paper by von Neumann. He says the following, he says, machines, automata fail, while logics are robust. We all know that if we write an algorithm on a paper, it will always work, even if it has bugs. But, computers are machines and they fail. And they fail us. And so von Neumann criticizes this and decides to remedy the situation. And of course, the remedy of him is not to abandon theory and mathematics, but to develop probabilistic logic of implementations that take into account the failure mode and accounts for it. In fact, what we have is that we have specification. Sorry, we have specification to implementation. Then the implementation behaves in a different way, so something has to be done. Oops. So the notion of side effect, that's another notion. That in programming language we have it, and in logics we don't have it. Like if Fortran, I'm old enough to remember Fortran. If you have a function f of x is x gets x plus 1. I know the notations are not pure Fortran. Then if you call in your program f of 1, then the constant, due to compilation, your constant 1 can become 2 throughout the rest of the program. And this is called side effect. So the question that all this raises is, what is the side effect of cryptographic implementation? The cryptographic implementation may have side effect, which is beyond the specification. I mean, the specification, the guy who wrote f of x equals x plus 1 did not mean that the constant 1 will become 2. But this is a side effect of the way you pass parameters in your compiler. So what is needed is that you have a wider implementation, and then you follow von Neumann. You don't say, oh, implementation, I'll call engineering to deal with it. No, you have to revise specification and go back to the mathematics. Because if we'll start getting out of the revised specification and doing implementation, we're going to lose it. That's a losing game. I'll talk a little bit, if I have time, about a little bit the philosophy, at least my philosophy, about practice and theory. So what was the interruption in the case? Where did I see the first interruption that led to malicious cryptography? Cryptography is a defense against bad behavior. It's a protection. But then I realized by looking at system that any security technology, when you add it to the system, you increase the system's attack vector. Many antivirus systems were used actually to attack systems. That was already known at that time. So therefore, cryptography also deserves a look from that point of view. And that's like who will guard the guard themselves phenomenon. And so if we have a security primitive, like encryption or some other cryptographic thing, in an extended or modified service setting, sorry, that may not follow only the model. You have a nice model, you have an attack, but it doesn't mean that the attacker always follows the specification of the system. Or you have a system and you say encryption, and you say, oh, you will use encryption when you want to protect your messages. But there's no contract between the user and the people that specify the encryption, that only when you need to encrypt information of yourself, you will use the encryption. Maybe you will use encryption differently. So either the setting or the application that you choose can do something with your implementation, can twist it in some sense. That was the initial thinking. you cannot guarantee that you minimally achieve only what you specified, but you may achieve more. That took some time in the climate of the mid-90s. And the first hint was of repurposing cryptography was actually a hint by the US government that they wanted to have escrow systems, and they built the Clipper chip to combine encryption with authentication, that the government agency can see who sent the message and then go to fetch the key of that guy that was deposited somewhere with judges that will release it and so on. So that was the first one. They had some design problem. The first one was MudBlaze that showed that the authentication field was small, 32 bits, and you can break it in on the average 2 to the 31 attempts. And then with my co-authors, we completely broke it. Escrow encryption systems visited attacks, analysis, and design. This was Crypto 95. We actually showed that the government cannot achieve, the way they design it cannot achieve this issue, because I can send a message the way I presented it in the conference. I send the message where the authentication field is the president of the US. And they will think that the president sent it, but the machines themselves will know how to decrypt it. Whoever designed it was very good in encryption and very bad in authentication, apparently. But that's an anecdote. And then the second hint was from my own work with Adam Young, cryptovirology, extortion-based security threats, and countermeasure. And this was not in the specification of the crypto system. This was in the setting where the crypto system was used. In this paper, we actually warned, predicted, and put all the ingredients that are going to be needed to develop what modern time is called ransomware. And we proposed also countermeasures. The current countermeasures are in the original paper. The current ingredients are in the current ransomware. Amazingly, we have a statement like this, that the internet has full connectivity, so it can come from anywhere. Or in the future, there will be an electronic payment system that will work, and it can be used to collect ransom in a much better and hidden way. Everything that you want was already in the first paper. So you can repurpose your encryption, and the idea was to use public key encryption on your machine to encrypt your resources. And if you don't have backup, then you're doomed. And you need the collaboration of the virus writer who has the private key to release your data back to you. Of course, it's still available on the internet, all the negative comments that we got from all the experts of viruses of the time. Shockingly, none of the antivirus companies implemented countermeasures. They were not so hard to try to do. But, you know, this is life. 15 years after, it became a few milliard $1 industry. So these were the initial hints. But starting in '96, we started to see how to repurpose cryptographic systems. And there are three stages. The first one, kleptography, or also known as algorithm substitution attack or subverted crypto. Then cryptography, which is to mitigate subversion. And then the more modern one is anamorphic cryptography. The first one is against the user. tricking the user. The second one is to take measures to protect the user. And the third one is even a step forward to attack the government who tries to violate the privacy of the user. And that's why they are kind of connected. So we'll see that all of them has the ingredient that you have correctness, security, but you also have side effects, as I said before. And so what is cryptography? So the idea was to have a crypto system that will be implemented for the user in a black box device. And one of the motivation was, at the time, the US government said that one of the way to deal with encryption is that the NSA, NIST, and AT&T will produce a black box encryption and will give it to people to use. So, so you have a black box implementation of a known crypto system, and what we showed is that there is a way that for anybody else, the algorithm, what it produces, looks indistinguishable from the algorithm without the subversion. And it will look okay to everyone but the manufacturer of the box. So it gives a unique, exclusive advantage. And we wrote in the first paper, some organizations would like to have this exclusive power. You know, that's always good to write such things, especially if the future proves you correct. But I don't mean to write one thing and also the negation of that thing. You have to go one way. So in the 96 paper, we did an RSA key generations with the factor hidden inside the composite representation of the public key. And later on, the year after, we showed it for discrete logarithm-based systems, both encryption based on discrete log and signature, and even in DSA signature, and so on. And it had some impact. And so we allow the attacker to modify the algorithm. This is algorithm substitution. It shows that the authorities or the manufacturer can get this additional advantage in these crypto wars. And this was, we started in Crypto 96 and continued to do it. And for example, the RSA. So RSA key generation, usually you have a fixed exponent, E, let's say 3 or 2 to the 16 plus 1. And then you choose, in number 1 there, you choose a large prime P at random, and then you make sure that you do primality test, that this is prime, and it is compatible, namely that the greatest common divisor of it and P minus 1, they are relatively prime. And then you choose P once it passes the primality and the extra acceptability test. Then you do the same thing for another number, Q, you choose random, another random number of 1024 bits in this example. You check the same thing, primality and acceptability. If they both check, then you just multiply them, and you have N equals PQ and E, and this is your private key. This is your public key. The private key can be a factor, can be D, an inverse of E modulo phi of n, which is p minus 1 times q minus 1. And that's the regular RSA. So in the cryptographic setting, we'll have the following. We'll have a black box environment. As I said, this is, let's say, hardware or software that nobody checks. And instead of just running the previous algorithm, first, so it will produce n equals p times q. P and q are 1024 bits, so the multiplication is 2048 bits. But there will be an extra RSA inside the box. And the RSA inside the box will be of size, half the size, 1024. And it will be a multiple of two primes, y equal y1 times y2, 512 bit each. Simple example. And so the key generation will not run the key generation choosing P, primality, Q, primality, and so on. What we'll do? Choose a large value S randomly, 1024 bits in this example. Compute P, which is hash of S, the cryptographic one-way function, like built on from hash functions, but publicly available. And it behaves like a random function, to the best we know. And of course, if P is not prime, it's supposed to be P from the previous implementation, namely a prime. If it's not, you go back and choose again. At some point, you pass 3, where P is a prime, and you go to 4. Then you choose a large value at random, I call it R and D, and you compute C, the ciphertext, to be the encryption of S. Remember, S is from step 1, is the seed for producing P pseudo-randomly, and encrypt it with Y, this seed, and we call it C. So C is the encryption under the attacker key Y, which is half the size, 1024 in this example, and that's it. And then you take C and R and D, the high order, look at it as interpreted those bits as a number, and you solve it for P and Q plus R integer division. So you have already P, so you do how many times P is inside this number plus R remainder, Remember integer division that we were taught in kindergarten. So that's what you do. Sometimes you have to go back to kindergarten in order to develop the right algorithms. So somebody don't like you to learn these attacks. Some people. It's here. Okay, good. Okay, of course, if the quotient, so now it's P and the quotient and the remainder. If the quotient is composite, start it again. Start from the start. Restart from the start. If it is, you get, then you declare n to be P times Q and the exponent, and it becomes your public key. It's 2048 bits. And remember, C with the random numbers equals PQ plus R, when P times Q is the N. N is available public because it's part of the public key. R, as a reminder, is about square root of N. So when we do this number minus R, most of this subtraction is going to affect the bits of R, and only the borrow bit, this is even pre-kindergarten, only the borrow bit will affect C. Sometimes you have to go even back in your education. It's good to have memory that goes back to pre-kindergarten. So the value C is not hidden much by the high order bits of N. And of course, hand waving, but with assumption that the function H that was choosing P is a pseudo-random function, and all the way Q was chosen, the likelihood of P and Q being prime, more or less, follow from the prime number theorem, plus the assumption of a pseudo-random function behaving like a random function. And there is a proof for that. You need a prime number theorem for that. And what does the attacker? The attacker who has the private key for the encryption Y, he computes two values. He comes here and takes the bits here, and either the bits themselves or the bits plus one should be the seed, because this is what we encrypted, the seed that was generated to generate the prime. So one of them S1, S2, I just call it, you take H over it, you get P1, P2, one of them should be your prime. Because this is the way we built N. And therefore, whoever can decrypt C, and you need the trapdoor of the Y, because it was encrypted under Y, you needed to know the factorization of Y, then you can extract the seed, and then you extract one of the primes, so you broke it. Who can do it? Whoever put his public key in the algorithm and kept the secret key to himself or herself. And this is the attack. And then we did it for other things. Only the attacker can recover secrets. We did it for discrete log, 1 out of 2, and then k minus 1 out of k. You can run k instances of discrete log where you can recover k minus 1 of them. People say nice theory. They accepted the paper for the theory conferences, but people in funding agency, without being asked, came and say, and I don't know if they did it on behalf of some organization or not, they say, oh, we prefer to finance more concrete and attacks. So this was nice theory until this guy came. And this guy came and said, here is another, the darker version of the dark guy. And this guy came and say in 2012, these are results from 1997, the dual EC, the deterministic random bit generation, which appears in my paper with Adam Young in Crypto 97. What they did, they implement this generator, implemented, you have to correlate two generators, and then this is the attack of the k minus 1 out of k. And that's what it was implementing. Namely, somebody who gave some generator G1 and some generator G2 knows the relative, the G2 is G1 to some hidden number. It's mod prime. It's a modular exponentiation. And somebody knows it, and therefore, from the random bits of the hello SSL, here are random bits, he can derive the next encryption of SSL. Okay, and then people say, we need to cope with it. And they started to try to clip down the power of klepto attack from 14 and on by many people. And we namely Chang and our co-authors and myself even had a paper that we actually name it Cryptography, clipping the power of kleptography. But there were other people working on, you try to have additional architectural components to cope with the attacks. And of course you want to have minimal addition to the architecture so you can solve it. And it took efforts of a few years to understand the wide range of techniques to try to cope with potentially subverted implementation. Yeah. So, yeah. So that was the name of the paper, Clipping the Power of Cryptographic Attacks in 2017. So it took a number of years. Like semantic security was not, semantically secure crypto systems were not known until this paper, how to reduce it in a easy way, only for certain crypto systems that are multiplicative, let's say, or homomorphic. So I'm not going to get into this because these are another 3 lectures of 1 hour each to do it. So as I said, we allow the adversary first, and then we reduce the power of the adversary, and then came 2022, but we started working on it in 2017. It took us 5 years to publish because we wanted to get all the notions and all the modeling and all the naming right so people will understand that this is important. We don't want another Snowden to come late to the game. So this is repurposing cryptography for the user's advantage, I mean, equity. So far we gave the authorities power over the user, and then we had to cope with it. Let's give the user power over malicious, no, I cannot call government malicious, but ambitious government. Okay, so what do we do with anamorphic? So whenever I give a talk, people ask me what is anamorphic. It's term in the arts, painting, statue, and things that you look at it from, you have a piece of art, you look at it from one direction, you see one picture, you look at it from another direction, you see a different picture. This is anamorphic. It is a second image. If you look at this can be just a flat picture. If you put perspective into it, there's a hole in the ground. If you put it on the ground, the dogs will move like this and we'll go around it. Here is another anamorphic statue. You look at it en face from the, you see a face. You look at it from the side, you see just hanging pieces. So it has anamorphic view. This is in the art. So it gives you second image in the same statue, second image in the same picture. So back to cryptography. Privacy is a human right. And it contributes very well to privacy, cryptography, and that is like end-to-end encryption, TLS, and so on. But all these rely on 2 assumptions that are implicit and not always stated. One is the receiver privacy assumptions. The receiver keeps secret its decryption key. It's very simple. We don't even say it in papers. It's obvious that you need it. And the sender freedom assumption. The sender is free to pick a message from a large enough message space. Because if the bad guy, the adversary, tells you which message to send, you don't need encryption. Or give me the key, you don't need to encrypt, because you know that the guy that you are protecting against already have the decryption key. And okay, but these are for, what we claim is these are for normal setting, and therefore encryption was developed under these assumptions. But what about a more powerful adversary? No receiver privacy. You have to give all your keys to the government. Do you know any government around here? No, not around here. I mean, the compromised place that between here and Melbourne that want to have everybody's key. Canberra, yeah. So no receiver privacy. Give me your key. Or no message privacy. Send this message. So these are assumptions that everybody made, and people say, oh, you have many assumptions in cryptography anyway, so who cares? No, but these are normative assumptions. These are not nature. These are not mathematics. This is not complexity assumption. This is, I'm not saying a legal requirement, because even Nazi Germany had a legal system. It's normative for society. So assume they don't hold in society. So we aim at places where they do not hold, and the question is how the user can retain her or his privacy. And that was the question. Can we do anything? And this is what anamorphic cryptography attempts to do, is about investigating existing crypto system, not inventing new crypto systems that immediately the government says, stop. Existing crypto system designed for the purpose of sending one key, and you are going to repurpose it to send a second key. And then if the authorities in the crypto war come to you and say even something ridiculous, send this message, you send it as one key, but you have an anamorphic message, which is the real key. Or they say, give us the key. You give them the key, but you use another key inside the same ciphertext. It's anamorphic. It's within the same frame. You know, the two pictures are in the same frame. It's in the same ciphertext. And of course, the crypto war has all kinds of argument that it creates naturally weak systems. Authorities argue against it, that they can keep the keys better than the user because the user uses PC, and they will put it in hardware in Fort Knox or in other places where government keeps secrets. But these are non-technical arguments. What we want is to see that cryptography by nature is easy to repurpose. If you put a cryptographic system like RSA encryption and you tell people use it, you allow the anamorphic use, the repurpose use, by definition. And the idea was to start a field in which to show it for all existing crypto systems. So that it's about the nature of cryptography, it's the functionality, is that you want to adhere to the specification of semantic security, you have an encryption, you adhere to it, it sends a message, aha, there is a side effect here, which is the anamorphic message. And that was the idea. So, for example, for anamorphic encryption, we will allow the sender and receiver to begin with, the first thing, to exchange another key on the side, or with steganographic means, time permitted, and then they share another key, and then they have two keys, and one key the private key corresponding to the public key will be one key, and then this extra key will be there. And when the authority comes and say, give us the keys, give us the key, you'll say, oh, here is the private key of the public key. And when they say, what about the anamorphic key? You will have deniability. I have no anamorphic key. Everything else you see is pure random. I'm choosing randomness. Of course, these are remote attacks. It's assumed the government doesn't sit on your computer, because if they sit in your computer, this is impersonation attack. You might as well go to sleep and they will do the work. But as long as they give you the freedom to run the crypto system, choose your randomness yourself, and they are just remote, and you gave them the keys, or you actually sending the messages that they dictate, or both, then anamorphic encryption will be enabled. The subject started in Eurocrypt 22 with Persiano and Fan, anamorphic encryption, private communication against a dictator. And when I give this talk in China, I say the dictator is the guy that dictates messages to the sender. That's why we call it dictator. Then, for example, in PETS 23, we had another paper with a number of co-authors, extra co-authors, the self-anti-censorship nature of encryption on the prevalence of anamorphic cryptography. In the first one, we showed two techniques just to stimulate people and ourselves. And in the second one, we already have a large list of existing crypto systems and standardized crypto system, and showing how to add the anamorphic. And the idea, again, is to have these two keys that send two messages and have anamorphic implementation be indistinguishable from regular implementation, even if you have the private key for the first message. So you can always claim, this is what I'm doing. So what I said is just written here. You have two messages, two secret keys, and the indistinguishability. And you have to prove all these things, of course, but we do. And it has to be an existing legitimate crypto system, otherwise either theoretical, if it's in the theory literature, or standard, if it's in the standard documents, and so on. None of the scheme was designed with anamorphism in mind. RSA was not designed with anamorphism in mind, all of them. And as I said, the adversary with the trapdoor cannot tell anamorphism from that the second message exists or doesn't exist. And the idea is that it's futile to control crypto system, because I give you the key and I follow your messages. Nevertheless, I'm using the system that you allow me to use in the system. I can use extra messages. And by now, we show it for many systems that are chosen ciphertext secure, in particular the systems that are based on the work of Naor and myself on CCS systems, Kramer-Shoup, Goldwasser-Mikali, Payet, RSA, this is standards, RSA OAEP, symmetric cryptography. Other people jumped and show it for post-quantum encryptions and things like this, El-Gamal-based systems. And it's like this. This is one example that I will not even do because I don't have time, but the NY system, you have two encryptions with two public keys. You encrypt the same thing, and then you have a non-interactive zero-knowledge proof that you prove the same thing. And with one key, PK0, you have the key, and PK1, it doesn't even exist. You throw it away. It's just a technical way to have the zero-knowledge proof, and this leads to the proof of chosen ciphertext security. What we showed is that, and so in the real use of the system, the second encryption is just the technical handle to prove chosen ciphertext security. For anamorphic, we use the second encryption instead of blessing the dictator, cursing it. And we have a simulated zero-knowledge proof, faking the proof that these two are the same. It's the power of cryptographic tools. We have to use them. So, and we don't throw the second key, but we give it to our beloved collaborator, and they can read the second message. When the government come and say, give us the two private keys, I say, oh, I have the one. The second one I threw away. I don't have. Perfect. This is an example of why in CCS secure system, you need this redundancy to be able to prove chosen ciphertext security. And then we use it for anamorphism. So, informally, why you can do it? Because cryptographic tools are powerful enough. I'll skip that, don't have time. Then we have also sender anamorphic schemes. This is when the authority comes to the sender and says, send this message. How do you do it? So we have results on this. We have various other techniques. Often the technique is, it's very simple if systems have randomness to embed the second system inside the randomness. So rather than use random generator and use it directly, you share a key for a random, pseudo-random permutation, and you apply it to the key and you claim to be the randomness. And the cryptographic strength is that this is indistinguishable from randomness. This is how you trick the adversary. And we also had public key anamorphic, in which you don't need even to exchange a second key. You can, casual user can come and use the system anamorphically and send me two messages. I'll skip the thing, and also you can do it even if the dictator is in the middle of sending everything and he re-encrypts for the receiver, you still need signature because otherwise the dictator can emulate anyone. So you need signature. And for this, we showed that you can have anamorphic signature that sign a message, which may be a ciphertext, which may be anything, but in it, it encrypts another message. So, doesn't matter, this is a bit technical. And I mean, the results show that two traditional signature constructions or families actually give anamorphic encryption inside the signature. So overall, our result gives technical evidence of the futility of the crypto war in trying to control cryptographic keys directly, because cryptography is redundant enough to be secure so that you can embed other things in it. Repurposing and thinking maliciously gives useful insight. Cryptography has naturally anamorphic properties because typically the ciphertext is not as strict and not at the same side of the message, and you can do things with it. So 4 years after, many people started to work on it. Just yesterday, I found a GitHub implementation for introducing anamorphic encryption inside the Signal protocol. Just yesterday. So things are happening on a daily basis these days. And there are many papers by us and maybe 10 other groups worldwide. And general conclusion in general about all these areas that I spoke about, the natural cycle of definition, design, implementation, and proof, and then systems